Hello, everyone. So this class, we're going to continue our discussion on the aerosol instrumentation. So this class, we're going to talk about the aerosol generation and calibration. Okay, so if we do a quick recap of our last class we basically covered the aerosol chemical analysis method. We first introduced the pills. So we mentioned that pills can do a lot of these offline chemical analysis. Pills actually act as an extractor to convert the aerosols from the gas phase into a liquid solution. But there are also limitations for the pills, right? So when we analyze the solution that's collected from this method, then we're only looking at if we're talking about the organic carbons, then we're only looking at the water-soluble organic carbons. The insoluble organic carbons will not be able to be homogenized into the solution and further get analyzed. We also talked about the instrument that can do carbon measurement, right? So elemental carbon, organic carbon. So by using the, let's say, basically baking them under different temperature, under different carrier gas composition, right, to analyze the EC and OC component. We also talk about single particle soot photometer, SP2, which measures the black carbon in real time. And then the majority part of the last class were about the aerosol mass spectrometer. So we introduced different components, the building blocks of an aerosol mass spectrometer. And also we talked about different types of implementations for the aerosol mass spectrometers. So this class, we're going to discuss the aerosol generation and calibration systems. So we have covered so many types of the aerosol instruments, but how do we make sure that they're actually measuring the right quantity, right? For example, we know that the size distribution are being measured by the SMPS. How do we know that let's say the differential molecular analyzer is classifying exactly 100 nanometer particles when we set it to be 100 nanometer? Could it be possible that there can be some minor errors or minor misalignment of the columns or different conditions that result in a different particle size, right? So that's why we need a calibration. We need to generate aerosols with specific sizes or specific chemical composition and send it into the instrument for the calibration, right? So this will involve both the aerosol generation and calibration. So we'll talk about the aerosol generation first. Overall, in terms of the aerosol generators, there are different types of them, but the most commonly used ones are listed here. So there can be atomizers or nebulizers, electrospray, vibrating orifice aerosol generator, fluidized bed aerosol generator, and aerosol reactors. So we'll just briefly introduce them one by one. So first about the atomizers, nebulizers. So the atomizers or nebulizers, based on how you call them, basically just convert, let's say, a liquid solution into droplets. And further, you can dry these droplets to remove the solvent in the droplet and then get the dried material. For example, you can use sodium chloride water solution, and then it will first generate these salt droplets, and then you can dry these aerosols or dry these droplets and further introduce or generate these dried sodium chloride particles. But how do we generate these droplets? Okay, so for the atomizers or nebulizers, what it does is that it injects a high pressure gas stream. Also note that this is not necessary to be high flow rate, you just need a higher pressure, right? So the compressed air will be introduced inside and then form this this straight gas stream going through. And then whenever you have a high speed or high velocity of a gas stream, it's going to create somewhat like a Venturi effect that create a low pressure zone at the side of the gas stream, right? And because of that, you can draw the liquid inside, and then the liquid will be brought by this relatively high speed, let's say, gas stream, and further get impinged onto a solid surface. Right, for example, for the nebulizer mechanism here, it's actually using the metal block as a surface for the liquid impingement. So once the liquid is impinged onto the solid surface, it's going to generate tiny droplets. The larger droplets will just settle down by gravitation, and then the smaller droplets will get carried by the gas stream and then further get introduced. So it's the same, a similar mechanism showing here, right? So you have compressed air, and then here they have a nozzle where you can generate this high-speed gas stream, and then it's going to blow the liquid, and then also fragment them, right? And further get impinged onto the wall, and then you can get these aerosols out. But we also need to note that when we generate, let's say, droplets, we didn't specifically control the size of these droplets. So eventually what we get from this impingement process is that we're going to have droplets of all the different sizes, right? And once they are further dried, they will generate aerosols or dried aerosols with a polar-dispersed size distribution. So here I'm showing you a few pictures of these example atomizers or nebulizers. So this is the atomizer that's manufactured by the TSI, right? TSI Incorporated. Here I'm also showing you two different types of nebulizers commercialized by the CH Technologies. So basically, for these, there are different configurations of the nebulizers, mainly for different purposes. For example, some of them you may need a high throughput of the liquid. For example, the CH type of nebulizers, they can provide relatively high throughput of the droplets. And the TSI atomizer can produce relatively smaller droplets. And then there are also types of nebulizers that used for, let's say, biological aerosol or bioaerosol generation. So for this specific type of nebulizer, it can avoid or reduce the foaming of the solution. So you get more consistent output of the bioaerosols. Right, so you can further optimize the performance of these nebulizers. But overall, they're using this method of using a high pressure gas stream to bring the liquid into onto a solid surface and further get these droplets. Okay, so this is about atomizer or nebulizer. So as we said, these atomizer or nebulizers, they don't have specific controls of the droplets, and also their droplet size is relatively large, normally in the range of, let's say, around 10 micrometers, which are quite large. And once they're dried up, so these droplets will shrink into, let's say, hundreds of nanometers, or let's say 60, 70 nanometers. What if you want to generate smaller aerosols? What about 20 nanometer, 30 nanometer? Right. So to do that, we need to generate droplets with smaller sizes. So to generate these smaller droplets, one commonly used method is the electrospray. So what the electrospray does is that instead of bringing a high pressure gas stream, we just use the capillary effect of the, let's say, of a liquid, that you have a very thin capillary that brings a specific liquid through the capillary. And at the same time, you put a high voltage onto the liquid, or you can also put it onto the capillary if they're conductive. Okay, so because of that, the liquid needs to be conductive as well, have certain magnitude of the conductivity. So because of this high voltage, and at the same time, the other side of the, let's say, the aerosol collector, or the, let's say, the section where you guide these aerosols out will be grounded. So because of this, let's say, electrostatic field, so the liquid will be drawn out, and at the same time, we're going to have a specific structure at the tip of this capillary. We have this, we call this specific structure as the Taylor cone jet. So it looks like a cone, and also when it's under the stable condition, it looks like a cone. And this is mainly because you have a high voltage being applied onto the liquid. And since the liquid is being pushed out, so due to the electrostatic repulsion, so the liquid is actually only getting injected through the tip of the cone. And then once the aerosols or droplets are ejected, these droplets will also carry a large number of charges. And because these droplets will go through the evaporation, their size will get shrink smaller and smaller until they cannot hold these charges anymore, because charges are going to repulse to each other, right? And that's going to lead to a breakup of these droplets. And once they break up, they're going to produce even smaller droplets that contains the salt or any component that you want to put into the liquid. So in this way, you get relatively uniform distribution of the droplets. And also these droplet sizes are smaller, which means that you can generate smaller particles. So the size of these droplets will depend on the flow rate of the liquid, the voltage that you apply, the nozzle diameter, and also the jet diameter. So these are the parameters that affect the performance of the electrospray. So you could also put some tiny components or any components into the liquid. For example, here is using putting the PSL particles. We'll talk about PSL later on. Basically, those are particles that have specific sizes and they're rigid, like plastic particles, right? So because the evaporation of the droplets is not going to affect anything on the PSL spheres, so you're going to see these droplets containing these specific sized particles once they dry up, right? You can see they have the size of 73, 102, and around 200 nanometers, okay? So this is about the electrospray, but at the same time, you see you can generate smaller particles, and this is because of the contaminants or extra components of these PSL spheres that are being generated by the electrospray. Another way to generate aerosols is called the vibrating orifice aerosol generator. So it's using the piezoelectric materials. So what happens is that we introduce the liquid into a tiny well right here. Okay, and at the same time, the piezoelectric material will basically vibrate under the certain electric signal, right? If they vibrate, then they're going to squeeze this volume periodically at certain frequency. And once the volume is squeezed, they're going to generate these tiny droplets, okay? So the advantage for this method is that they can generate relatively uniform sized droplets with specific diameter. And then this diameter is also related to the, let's say, the working condition of this vibrating orifice aerosol generator. For example, the flow rate of the liquid, the frequency of the vibration, and further, once these droplets dry up, they're going to expose the dried materials, let's say the salt or any other type of materials. And then the final particle diameter is related to the concentration of the, let's say, these components in the liquid, right? So basically, this is how the vibrating orifice aerosol generator works. So what if, let's say, you want to generate non-soluble materials? So we have been introducing how to compare or how to generate aerosols out of a solution, right? What if you don't want to generate aerosols from a solution, right? What if you would just want to suspend some dust or sand, and you also want to get a relatively constant output of the aerosols? So this is where the fluidized bed aerosol generator came into the picture. So what it does is that it uses a fluidized bed and then use a lot of these beads here, and then basically people will introduce the air into this volume, this fluidized bed, and then it's going to suspend all of these let's say pre-cleaned bronze beads, right? So they're going to suspend, and these beads have pretty large diameter, which means that by gravitational settling, they will just settle down. At the same time, there's a cyclone here to remove all of these larger beads here, right? Prevent them from going out. At the same time, if you want to suspend some dust or some, let's say, larger aerosols, for example, the coal particles or like tiny road dust, then you just need to put those materials into the other reservoir. At the same time, there's a rake that's keep going, right? It uses the tiny spacing between these tiny rods here or tiny spheres here to bring the materials into the other chamber, the fluidized bed. And then since these beads are always moving, right? Although chaotically, but it's also uniformly, relatively uniform movement of these beads. So they're going to suspend these dust particles into the chamber here, the fluidized bed here, and then get further generated. So the advantage for the fluidized bed aerosol generator is that you can control the feed of the dust you put into the fluidized bed generator, right? Basically, you can control how fast the rake moves, right? And further control how much particles you put into the generator, okay? So we have been introducing these methods that either convert liquid into aerosols, or but through evaporation, or let's say through the physical process of suspending it. There are also other types of aerosol generators that relies on, let's say, the phase change or relies on the chemical reaction to produce the aerosols. So here I'm listing a few more examples. For example, you can have the tube furnace, where you can generate some aerosols that have relatively low boiling point. For example, you can use ammonium sulfate, and you can generate them with the the nebulizer first, and then once they're introduced into a tube furnace, these ammonium sulfate particles will just vaporize. Okay, they get into the gas phase, and further, when they get out of the furnace, people can add on this dilution section, which reduce the pressure, but at the same time maintain relatively high supersaturation for the ammonium sulfate, ammonium nitrate. And then these vapors are going to nucleate and then form particles. So you can control the dilution process where you can minimize the size of these ammonium sulfate particles. So their sizes after this nucleation and initial stage of coagulation condensation will be much smaller compared to the method where they're generated from the nebulizer directly. People could also use the hot wire generator. So basically, these are going to use some metal wires that has also let's say emit vapors when they have a relatively high temperature. People can use a tungsten material or iron or any types of metal, and then you subject them to relatively high power by introducing, let's say, applying a voltage or going through a current to warm them up. Normally, they will be under like a hot, let's say, they will show color, right? It's just like the conventional light bulb that we see. So basically, the temperature is high enough that they're going to emit these metal vapors, and then, or they can get oxidized and then further form aerosols. And you can form relatively smaller aerosols as well. So I think this is also another type of the furnace aerosol reactor. And then we could also use combustion to generate aerosols, for example, the soot particles or many types of the metal oxide nanoparticles. So we have talked about these aerosol reactors. So get back to the question that when we want to calibrate our aerosol instruments, we also need to provide the materials for us to calibrate them, right? So this involves the size calibration. So currently there are three major types or three major ways for calibrating the particle sizes. The most commonly used one is the polystyrene latex or the PSL spheres. People also use the electrospray to generate tiny organic ions when we're trying to measure particles with very small sizes, let's say below 5 nanometers. And for the larger sizes, if we don't have access to the polystyrene latex or PSL particles, we could just use the polydispersed aerosols and DMA if we know that the DMA is already calibrated or is accurate. So first we can talk about the PSL particles. So PSL particles are made by some chemical engineering processes, which basically grow tiny plastic particles in a solution. And then because these processes are well controlled, it's through the wet chemistry, their size is actually very accurate. And they have this perfect sphere structure. And you can also control their sizes. And they can be as small as 30 nanometer, as large as 5 micron. And then since we know that their size is well controlled, we can use these PSL particles as the size standard for calibrating the aerosols. So what we do is that we can dilute this PSL solution enough so that they form a very dilute liquid, and then we can further disperse them through atomizer, nebulizer, or electrospray, and then these droplets will further dry to form a single sphere, PSL sphere in the droplet, and then we can further measure their sizes. So they can also be generated by, or basically they can get generated by nebulizers or electrosprays. So we could also use the electrospray of the organic ions when we're trying to generate aerosol standards with much smaller sizes. So for example, here there are a few example types of chemicals that basically these specific chemicals are made of ions, but at the same time, they're made of these halogen ions attached onto a very long organic component. So organic component will have multiple, let's say, hydrocarbons, or maybe 20, 30 hydrocarbons, but they have very pure component. So because of that, when you generate these ions through the electron spray, then they're going to retain this specific structure. They're going to have a very uniform mobility size, right? So if you see from their mobility distribution, they have very sharp peaks here coming out of the electron spray. And you can see that based on their electrical mobility, they have sizes of, let's say, between 1 nanometer to, let's say, 3 nanometers. And we could use these organic ions as size standards when we're trying to calibrate, let's say, DMAs with higher sizing resolutions. So the third option is to generate the polydispersed aerosols and then further classify them based on the DMA. So this method is also quite widely used, especially when people are trying to calibrate the accuracy of another DMA or to calibrate the accuracy of the CPC, the condensation particle counter. So for example, you see people are using this furnace aerosol reactor, the electrospray, the wire generator, all with the purpose of generating small particles of around 5 nanometers. But actually, it's not limited by the size. It's just this application is just for calibrating the performance of the CPC. So you can use the DMA to generate aerosols with very tiny sizes. And then at specific sizes, you can calibrate the performance, like the detection efficiency of the DMA by just comparing what's being detected by the CPC and the electrometer current, because we said that the current of that's monitored by the electrometer is related to the concentration. Well, not all of the particles are being detected by the CPC. So by using this method, we can determine the detection efficiency of the CPCs at different diameters of the particles, right? So you see this detection efficiency is also dependent on the chemical composition of the aerosols, and it's related to, let's say, it's also a very strong size-dependent curve. So that's it for this class. It's a really short class about aerosol generation and calibration.